With that, I'm really happy to bring on these visionaries. I got a chance to talk to them all last week at an invitation-only HPC AI and quantum conference called the Salishan High-Speed Computing Workshop. And so they all agreed to be on this session today, and it's a really good time coming out of that workshop and before the Trillion Parameter Consortium meeting and the International Supercomputing Conference to sort of take stock of where we are and think about how fast things are moving. So I want to welcome Tuk Kwong from the Department of Energy at the National Nuclear Security Administration, Dan Reed of the University of Utah, and many other roles before that, including leading NCSA, and of course our own Bill Magro of Google Cloud, who you've seen in this series before. With that, Tuk, will you tell us just quickly a little bit about yourself?
Great. Thank you, Jay. Hello, everyone. I am Tuk Kwong. I am currently serving as the Deputy Assistant Deputy Administrator for the National Nuclear Security Administration. Sorry, I got that word. Within the Department of Energy. So my office is Advanced Simulation Computing Program, which is one of the 2 high-performance computing programs within Department of Energy. I am a long-time career vet since '92, and I've been with my program since December 1995. Most recently, I served as the NNSF Federal Program Manager for the Exascale Computing Initiative, of which we procure the El Capitan system, which is right now deployed at Lawrence Livermore. Jay asked me to list other major projects that I've been lucky to have had experience with. You can see that I have been just mostly in the high performance computing world, but my program is the program that works on high performance computing, AI, quantum, neuromorphic, in addition to the nuclear weapons application development for NNSA. Thank you.
Thanks, Tuk. Dan, tell us a little bit about yourself. Tell our community about you.
Sure. Well, nice to see everyone. I've done a variety of things over the years. As Jay mentioned, I was head of the National Center for Supercomputing Applications. Back in the late 70s, I had this crazy idea that you might be able to build supercomputers out of microprocessors. And, well, nothing ever came of that idea. Built the NSF TerraGrid, which is still, its descendants are the drivers for most of the government-sponsored computing infrastructure for scientific research in the country. Built a research center in North Carolina that drew on computing to address societal problems called the Renaissance Computing Institute. Went off to Microsoft, and at Microsoft, I was there in the early days of cloud computing, built a lot of hardware prototypes for energy efficient computing. Also at one point owned Microsoft's quantum activities, and then also in the later years ran international technology policy for the company. I just retired. I was the chief academic officer at the University of Utah. Ran a university through COVID. I wouldn't recommend that. That was not a lot of fun, but it was really important. And I spent a lot of time on government policy over the years, both the President's Council of Advisors on Science and Technology, was chair of the Advanced Scientific Computing Advisory Committee for the Office of Science at DOE for many years, and just recently ended a term as chair of the National Science Board, which oversees the National Science Foundation, which is a basic research funding for a broad variety of disciplines in the U.S.
All right. Thanks, Dan. And our community probably knows our fearless leader, Bill Magro. But Bill, why don't you say a few words for the new folks about your role at Google?
Yeah, and apologies, I did not prepare a slide, but a little bit on my HPC background. I started as a grad student in 1989 or 88 and at NCSA doing many-body quantum physics, and that's where I cut my teeth on HPC. Between that and then later a postdoc at Cornell Theory Center, got exposed to essentially all the major parallel computing platforms of the day, everything from the Crays and vectors out to CM2, CM5s, the first IBM SP, and so on, the T3D, the T3E. So I shifted into industry in '97 and got acquired by Intel. And to Dan's point, showed up and said, "Hey, we got cheap processors that get the right answers. We should be able to build something out of this." So inspired by the Beowulf movement of the prior 4 or 5 years, decided that I wanted to see if we could bring that into the commercial world. So I initiated Intel's, I'll call it modern HPC business, because there had been a prior HPC business, and spent 20 years at Intel, eventually becoming Intel Fellow and CTO for HPC. In 2020, I moved to Google to help build the HPC business and lead it, which is where I am now. So some fun facts and maybe some HPC technical contributions I made over the year that folks might not be aware of. I built my first own x86 system back in 1989 using Linux version 0.98 patch level 2, and I downloaded it on 30 floppies at the UIUC computer center. And that's because the modem connections at NCSA were so slow that it was more productive to port MPI to Linux and PVM to Linux and TCM MSG to Linux and do my parallel programming on a 40 megahertz AMD processor. After that, I came up with the idea and built the first InfiniBand cluster in the industry and demonstrated that in collaboration with Rob Pennington's team at NCSA, who worked on the software with my team.
Yep.
And I'm the lead inventor and patent holder on some things that are still relevant today, like the first fabric independent MPI, RDMA over Ethernet, and I think crucially, the ability for accelerators to talk to each other directly through RDMA with host bypass. So what's known these days affectionately as GPU direct RDMA. And then I was the co-chair of the InfiniBand Trade Association for 12 years, from 2007 to 2020, when I left Intel jointly with Mellanox, and we oversaw a lot of the innovations around speed bumps, faster encoding, signaling improvements, error correction, virtualization, and Rocky, which were all critical things to make InfiniBand actually work in an HPC environment, even though it was not made for that. And then finally, I conceived and initiated the transition in the industry from Open Fabric's verbs or InfiniBand verbs to libfabric to open up for more innovation in the interconnect space.
All right. Well, our audience can certainly see that we have an experienced and expert panel here with deep roots in high performance computing. And as with AI emerging and quantum technologies emerging, they all have exposure to that as well. So now we're going to jump into our questions for them. And I've worked with the panelists ahead of time. We have about 10 questions. So I've asked them all to give sort of maximum 1-minute answers each, times 3 panelists. That should give us about a 30-minute conversation or so, and give you, the audience, some great key messages about each of these technologies. We're going to start with classical HPC. I've got a couple of questions for you. So we're well into 2026, and both of you have mentioned the transition to commodity microprocessors, Dan and Bill, and took, obviously, your agency is leveraging these. In some ways, HPC doesn't look all that much different than when we made that transition. We've got x86 processors, low latency intercommunication fabrics, and parallel file systems. So one view might be, has HPC really evolved that much since then? But we can point to some incremental and maybe not minor changes, like adding ARM accelerators, ARM processors, adding accelerators, advances in networking between accelerators, new programming languages like Python and Julia and Mojo, the use of Jupyter notebooks, the use of containerization and Kubernetes, new kinds of storage systems in addition to parallel file systems. Do the sum of these modifications and new technologies, do you think that it's radically changed HPC since the advent of microprocessor-based HPC clusters, or do you think it's really just a steady ongoing drumbeat and the major advances are still to come through AI and quantum? Bill, why don't we start with you on this?
Okay, well, I mean, you helped us answer the question by listing like 10 things that have changed, but I actually think the world is dramatically different. I think we saw that we were hitting a wall with the typical, 3 orders of magnitude every 10 years. Back around 2006-07, you could see it in the top 500 list. This is what led to the introduction of accelerators. But software moves slowly. It's been, I think, we're coming up in the 27th year since the Keeneland project and the DOE initiated to say, could these things work? And if you look, the vast majority of software in HPC still runs on CPUs and CPUs only. There's obviously a lot of bifurcation where the high end has adopted accelerators, but there's there's this whole long tail of folks who haven't. So that's been a dramatic change, and you really have to re-architect for GPUs or accelerators. You can't just recompile or read a compiler output like you could for vectorization or some other things. So that on that front, that's been a huge change and still a challenge, but I think AI is going to help us over that hump, and we're starting to see it. On file systems, I think there's also been a dramatic change. We've seen Lustre getting long in the tooth and new things inspired by cloud storage, such as Deos and Weka and Vast, and new things coming from VDN. So the storage world is changing, and of course the scheduler world and the whole notion of resource management, who's in charge, Kubernetes versus something Slurm-like, and how they coexist is another massive shift in the industry, not to mention cloud.
Okay, Dan, what do you want to add to what Bill just said? And the real question is, do you see this as steady, incremental, but important incremental advancement, or do you think the sum of these additions has given us revolutionary new HPC capabilities?
Well, I don't know about revolution. I agree with Bill that it is qualitatively different. Actually, one of the things I would say is that if you look back at the old days, they were quaintly simple by comparison. One of the things that I think is really important is the rise in complexity, and you enumerated some of those. And so I think in many ways the entry barrier at the high end has become a lot more complex. Bill's absolutely right that the bread and butter is maybe as we used to say when I was at Microsoft, less about the top 500 than the bottom 500,000. I mean, that's where the day-to-day work gets done by most people. I would say the big changes I see are more complex multidisciplinary workloads. Early days, it was really largely a single discipline. The other is the increasing need for real-time response. The batch model it still is important, but real-time data assimilation is increasingly important. I know we'll talk some more about AI later on, but I agree there is some bifurcation between the really high end and the mainstream in terms of GPU adoption. I think the thing I worry about most is that as we see the end of Moore's law, and you can argue about that, but we certainly saw the end of Dennard scaling. Right now, if you want more performance, frankly, it means pour more money into the machine at the high end. And that free lunch that we had for 20 years is really over. And so there's real pressure for us to innovate in some technologies to try to recapture some of that performance gain. Because I don't see a scenario in which trillion-dollar computers are available for general science. They may be for commercial purposes, but it's kind of hard to see that for curiosity-driven exploration.
All right, and Took.
Yeah, I wish it was a steady drum beat like you used, Jay, because it's totally not. Just adding to what Dan just said, it's much more exponentially complex, especially for my program. We started the office in 1995, the ASCII program that some of you know very well, and that was the start of MPPs, right? And I started my young career managing vendor partnerships, software tools like the Etnis Total View Debugger, right? And so to Bill's point about figuring out how to do the resource management of both the hardware capabilities and software services. It's not just allocating the nodes, but we need to also have to think about memory, file system that come along with the compute. When we allocate these jobs. Bill mentioned about porting to GPUs. It took us my program with the Livermore Sierra system that has the IBM Power and NVIDIA GPUs. In the 2017. Now we are, I think, near finishing our application code base to GPUs, but there are some codes that we've made the decision that they will not ever be ported to GPUs as we know now. It's just not optimal. So code porting for a 3-decade-old program like mine is a huge decision that we have to make in terms of continuing to modernize, to upkeep our codes, and also to develop new algorithms, new programming technologies, so that we can attract young staff members to join our national labs, to join my office. So the world is much more complicated. And mentioning just like and going to the fact that compute and ModSim now is no longer just the high performance computing, big scientific versus the small, right? We'll touch on AI soon, but that adds to the complication.
All right. I've got another HPC question for you, and I'm going to remind everybody, try to keep answers down to about a minute because I have so many AI and quantum questions coming up. So I want to make sure we get through as much as we can. For the next one, just what is your greatest concern right now about the ongoing advancement of HPC infrastructure and or software and or expertise? I'd like to get each of your top concern from the ongoing advancement. You oversee a very large program with thousands and thousands of users. What's your number one concern area for the ongoing advancement of HPC?
Decreasing buying power. I cannot spend more money on buying GPUs because I need from the same source of funding for my laboratory workforce to do the software development application, same funding source for my vendor partnerships.
Well, now I feel guilty asking Bill, who bought all those GPUs. Bill, what is your number one concern about the future of HPC?
I don't remember buying any GPUs. Maybe some of my friends did. Mine is actually related to GPUs and accelerators in general. I think we all know that the early work from the DOE to show that GPUs could do high performance computing led to the supercomputers. And around 2012, that led to the resurgence of AI, people realizing 20-year-old algorithms could actually work at scale. We're in a stage right now a phase right now in the industry where AI is driving the future of AI and HPC architecture, and it's driving us to lower precision and higher performance, which is what AI needs. And I think we've got a coming crisis for the scientific community, even though maybe we're already there, where we have to figure out how do we keep making HPC faster for ModSim in a world where we don't have increasing performance on high precision floating point.
Great. Dan, what is your number one concern for classical HPC?
It's actually related to something that both Tuck and Bill just said. The ugly truth for a lot of complex multidisciplinary HPC applications is we get single digits of the peak hardware performance on those applications. And it's largely because of memory bandwidth. We're memory bandwidth starved. And yeah, clever algorithms can deal with some of the low precision of Zaki scheme and others. There are some techniques and there's research in that space, but I worry about the low performance. I worry as well about, and it's related, that the pace of hardware innovation in the cloud sector and AI runs a real risk of leaving traditional HPC ModSim behind, both because of divergence of software stacks, and that's a concern, but also just the pace of innovation in the hardware.
All right. Dan, I'm going to start with you on this one. AI is clearly the major technology driver of the economy right now, and it's becoming a major driver in science. How are you seeing the science community embrace AI most effectively? And I know that they're using it in many different ways, but what's one success you're really seeing, one area in which scientists are really using AI effectively?
Well, I think the biggest one, without doubt in my mind, is the use of surrogates. It allows people to do parameter studies at a scale that historically wouldn't have been possible. So compact models that have been trained that you can use. Of course, as George Fox, the statistician, said about models, all models are wrong, some are useful. The danger about surrogates, as it is with any model, is that you push it outside its domain of applicability. But you can see that in so many areas, from weather forecasting and just in general ModSim, where that substitution has expanded the range of possibility. It's in some sense a price performance multiplier because you need a lot more hardware to do the same thing than you can in some cases now.
All right. Took, how about you? I'm afraid you might also be thinking that, because I know DOE is big in using AI for surrogates already. Is that what you see as the #1 scientific success of AI?
Oh, I think it's one of the #1 successes so far. I think we've been using, our big simulation data sets as surrogates for AI training. And for the last few years, my own program, we've already embarked on the AI for design, AI for manufacturing applications to meet our NNSA needs. And it's due to the fact that right now, NNSA, the Stockpile Stewardship and Management Program, we have a much bigger scope for the Department of War. And so we are looking to use AI to help us do new manufacturing techniques, better and faster qualification process to be, more modern, using AI for defect detections of our components. And so those are the things that are, they are scientific, they are engineering, but they are also very real right now in our enterprise.
And Bill, I know that you're familiar with Google's slew of AI technologies, from individual productivity to knowledge discovery. What do you think is the most important early success of AI in science?
Well, I think there's two lenses to look at this through. The first one is most effective and impactful, and the other one is most prevalent. And so I think I agree with Dan and Took in that in terms of current impact, these surrogate models are probably the most high impact things, and we can see it through, at least on the Google side, things like WeatherNext and AlphaFold 3, where we're able to build models. But basically, there's a big challenge in the industry is a dearth of data to train these. We're lucky enough to have access to years of climate and weather forecasts along with outcomes. We're lucky to have access to DOE's protein data bank. Without that, these things wouldn't have been possible. Most companies who want to build surrogate models don't have that privilege, or that what's the right word here? They don't have that ability, and so that's what's blocking it. So in terms of most prevalent, I honestly think it's scientists starting to use things like deep research and the deep thinking and reasoning models to accelerate their ability to sift through the literature and challenge, learn, and then also develop their own hypotheses and test their novelty in terms of prevalence.
Awesome. Next question is the far-reaching AI question. How do you assess the long-term potential of this? Do you believe that these LLMs and the foundational models we're creating have a long runway, or do you see any other emerging trends in AI that you think will complement or eventually replace them? And maybe the longest range question is, do you think the path we're on is the path to AGI, and does that even matter? And I realized I just asked a very open-ended question while asking everybody to give minute-long answers, but do your best on this. The state of the near-term future for LLMs and foundational models, and the long-term future. Bill, why don't we start with you on this?
Okay, well, I think, just continuing on what I was saying before, I think for us to get to a world where we have surrogates who can really become reliable, verifiable, or we know when they do their own uncertainty quantification, is going to be a long road. You look at industries like electronic design and computer-aided engineering, more on the industrial side. Just there isn't that body of available information that was used to train the LLMs. But the path I think we're on is an agentic future. I think we're seeing already amazing things where people create surrogates for applications that can learn runtimes and inputs. And and so on. We see innovations like Alpha Evolve, where a system can interact with a code base or a design and move it forward in material ways, and sometimes very innovative ways, novel ways. And I foresee a future where, every scientist has their own, I hate to use the term co-scientist because it's already been coined, but their companion that makes them more effective. So I see us kind of in a world where these multi-agentic systems are accelerating the pace of discovery and also helping us discover the negative results, which are so important in research earlier. So fail fast and move forward.
All right, Dan, let's go to you on this. Short-term and long-term for these transformer-based methods of AI.
So I think one of the things to remember is that we as humans in the near term tend to overestimate change, and in the long term we underestimate it. So, as you think about impact, that's something to keep in mind. I agree with what Bill said. The other part of your question, I'll start with the long term. I'm dubious that we're on a path to AGI using the current technology. I actually think we need more fundamental research in brain science, because we really, I think brain-inspired computing is maybe the qualitative change at some point. That's a long-term bet. In the near term, I think the other thing we're going to need to think about hard is automated laboratories, and all of those V&V things, validation and verification issues that Bill mentioned, come into play. I think the other thing we're struggling with is the explosion of what I would describe as mediocre results. With the ability to rapidly produce things, another aspect of V&V is how do you find the wheat in the chaff, right? There's a lot of noise out there right now, and being able to extract that is really important.
And Took, let's close this question with you.
I would add that for us, we look at small, medium, large. We cover the whole span of the language model space, just because, for us, we need to develop our own internal, classify, right, models, but to do that effectively, cost effectively, and performance wise, we need to partner with our external academic and industry communities and learn and just customize the models wherever is necessary, and bring them into our classify side. With regards to long term, right now we are responsible for both strategic and tactical research and deployment issues. So I'm not sure, we can afford to think as far as Dan has mentioned, but I think agentic AI is something that is in our near future and will hold a lot of promises for us, from which we will learn and figure out how to do more of the automated digital thread workflow management, right? And I brought up the staffing issue before. That is going to be probably one of the key drivers for our AI program, and how to continue to meet a mission with the new generation of employees who refuse to work in, our secure, work environment. So, yeah.
All right. I'm going to jump to quantum computing now. We've seen a rise in government funding globally for quantum computing. We've certainly seen some incredible valuations, investments in and valuations of quantum computing companies, and yet it's not ready for prime time today. I want to ask you each to give me sort of your 1-minute view on where you think we are in quantum computing, and what it's going to take to cross that hurdle, and roughly how long do you think it's going to be before it's going to be useful to the kinds of customers in Bill's case and users in Took's case that you're familiar with serving with HPC and AI. But Dan, I'm going to start with you on this. as the retired guy who's seen it all and seen all these technologies rising and everything, tell us what your objective perspective is on the prospects for quantum computing.
So first, I would say I don't foresee quantum as a replacement for general purpose digital computing. I think it will remain an accelerator for some very pragmatic reasons. There are real issues about crossing millikelvin barriers in order to transmit data. It's not real great at real-time data assimilation. It's great for the old life, the universe, and everything 42, where you compute a long time and there's not a lot of I/O. There are lots of material science and other quantum-based models where I think it's going to be incredibly useful and important. How long? Boy, I don't know, but I think it's more than 5 years before we get to that point you were talking about. Because you noted we're a long way from the logical qubits that would make it an everyday process for Joe or Jane programmer out there to be able to develop quantum algorithms on a system that they can trust the answers.
So super important, but for a certain set of problems, not all, and more than 5 years out.
Right.
Great. Took, what about you?
I totally agree with Dan. With my program, sort of like spearheaded the exascale bow wave, whether it was for the right thing or the wrong thing. I am so glad to not have to also be leading on quantum. I defer that to my peer in DOE Office of Science and the DARPA QBI program, and I am fully behind them for achieving their goals of 2028. Dario Gill's public statement for 100 qubit error corrected, right? And then, the DARPA's QBI 2030, 335 utility scale quantum system. We are tracking down those goals. We are working with those agencies and others very closely. And we, within my program, we are working on the algorithm side, and working on some few specific application cases for those quantum technologies. I want to say that with quantum, it's going to be a rather very interesting research area, because quantum technologies vary and their benefits are very much dependent on the technologies, on how you're going to use them, how you're going to host them on site or off site, right? So that's going to be a very, very fervent research area for young people.
Took, I couldn't agree more. I think it's fascinating that we make all of our classical microprocessors effectively the same way, but all of the quantum units are based on completely different atomic and subatomic particles, leveraging the same quantum physics, but by using different particles in different environments, you get very different characteristics, speeds and fidelities and things out of these. So it's going to be interesting to see whether we have one quantum modality winner or multiple for different kinds of problems or something. Bill, since your PhD is in quantum physics, as I recall, and you work for a company that makes a quantum computer, what do you feel like is the prognosis for this really impacting our Google Cloud customers, sort of time scale and scope of their domain space?
Well, I think one thing that's important to know is that, Google is a quantum computing company. It's a different part of Google, cousins to where we live in Google Cloud. And they have their goals, and just like Took, it's I'm leaving it to my peers to see how fast they can advance the state of the art. I think there's some exciting stuff underway at Google and across the industry. I want to emphasize Dan's point. Quantum is not, and I don't see it ever being a replacement for classical computing. The I/O is one factor. The other is there's just a dearth of quantum algorithms to solve important problems. That's a key area of research, and I think that's where cloud comes in. Which is to develop the quantum computers, everything from the device physics all the way up to the algorithm development, to looking if you can take, say, ensemble approaches in non-error-free quantum computers and still extract useful information, is a high-performance computing problem. For example, if you want to run even a 42 qubit simulation, you're up into the petabytes of memory, which means a supercomputing problem. So that's where cloud can help, is to advance the state of the quantum computing industry. And then once quantum computers are there and available to solve problems, I see an integration with classical supercomputing into hybrid workflows. I think Dan touched on that as well.
Great. So Dan and Took, I'd like to ask this next question of you. What do you think Google Cloud, what can Bill and I and our team and our broader Google team, what is one thing you'd really like to see us contribute by this time next year? If we repeat this panel next year, what is one thing you'd really like to have seen us accomplish in HPC, AI, or quantum, or the convergence thereof? Dan, let's start with you.
So one of the things I think that's really important to realize is that the cost of cloud infrastructure is really, and I don't mean price, I mean cost, is problematic for much of the scientific computing community. As we see the rise of hyperscale growing, and I say this from my Microsoft days too, it's priced out of most of the public sector at the large end. And much of what's cool and happening in AI and other things is largely the domain of folks in the private sector. So how we bridge that gap in some creative ways of public-private partnerships that protect the profit opportunities for companies, but also bridge that gap. So if you want to play with the cool toys, you don't have to go to work, just go to work for a Google or a Microsoft. That's important, but how you bridge that gap in ways that allows the US to remain globally competitive, as our global competitors are working in this space too. That, I think, is a geopolitical question. It's more that than technical, but I think that may be more important than the technology issues. I could enumerate a lot of those, but I won't in the interest of time. We've talked about several of them.
No, that's a great point. Tuck, what can Google do for this community over the next year?
So as a federal program manager, I'm gonna say my answer applies to Google, but it also applies to any of our vendor partners. And I'll add my technical spin to Dan's comment. We need our existing vendor partners, potential vendor partners, to understand our environment, which we have invested for 3 decades. We continue to have to build on it. We cannot walk away from it. So, and some of you have been working with the NNSA labs that are funded by my program. You'll know that we have very, very specific requirements with the cyber, with the work flow management, right, with the compute environment, and things have to work smoothly or as transparently as possible. So we always require a lot of, let's just say, contacts for kind of meetings to explain for months, what are our operational requirements for a new technology or system, or even software to be added to our environment. That is always a complication, and I think with the cloud service providers like you all or others, people just hear, oh, we just need a classified compute environment for cloud, but once we start talking, it's much more difficult, just because our users are very demanding, or maybe even high maintenance. So it's a special requirement that your services and capabilities have to align well with ours.
All right. And final question before I get into audience questions is, what is your top recommendation, each of you, for our listeners, for the viewers of this, and more broadly, for the global community of users of these technologies that may watch this video on YouTube later. Bill, since you didn't get to answer that last one, I'm going to start with you on this one. What's your number one recommendation for anyone who might watch this beyond the session or watch this video?
I think the pace of innovation in agentic systems is mind-boggling. And while I think those of us and most of the people on this call probably are exposed to the news, I would bet a much smaller fraction have actually been able to take the time, just sit down for 4 hours some evening after you put your kids to bed, and and play with the tools. There are amazing tools out there that you can play with for free. On the Google side, those are easier for me to rattle off. Things like anti-gravity, deep research, notebook LM, aistudio.google.com, where you can play with different models, just play with these things and learn a little more about prompt engineering, because the quality of what you put in, the classic garbage in, garbage out, really does apply in AI, and start to discover what's happening with these tools and also in the world of agentic systems, including enterprise features that makes it safe for you and secure for you and auditable and traceable, to build systems that can really make your workforce and yourself more productive.
I love that, because with no prompting, that leads perfectly into our next two sessions for the Google Cloud Advanced Computing community. So I hope people will tune in for those. The next one's on personal agentic systems, and the one after that is on building enterprise-grade agents using Google's technologies. Couldn't agree more, Bill. I think
I should have looked at the calendar.
Oh, you did look at it. Okay.
No, I didn't. Apologies.
So, actually, Forbes just put out an article today that supports what you just said, quoting Microsoft researchers saying that we're getting a growing gap between the aggressive AI adopters and the ones who are taking their time learning it. So it's moving so fast and the capabilities are so great that if you fall behind, you're really falling behind. So I encourage everybody to keep up. Took, what is your number one recommendation for our viewers and for the community overall?
Continue to exercise your critical thinking. Right. Just because, yes, I mean, new technologies, new toys are really fun. And I think that is the upside of some of our very, very, heavy duty jobs. But at the same time, we always have to question, is it actually delivering what, what the real result should be? And I think Dan and Bill mentioned, verification, validation, UQ, right? That should also be applied to what we use, AI, for, our personal life. Don't trust everything that you see, right? That you get. But at the same time, don't, stay behind and not, embrace it, learn it, know more about it. But you still have to question it.
Yeah, and I loved your beginning emphasis on maintaining your critical skills thinking ability. I know we discussed that at the Salashine workshop last week. I know that Forbes article I just referenced mentioned that the aggressive adopters are also aggressively keeping their critical thinking skills sharp. So they're finding that balance in that as well. So I love that. It was also the topic of a Scott Galloway podcast this past week about if too much dependence on it is not good for you, even if it makes you more productive in the short term. So critical thinking and the use of it as well as maintaining critical skills. Thanks to Dan. Final comment here. What's your recommendation for our community?
Well, yeah, Bill hit the pace of change, I think, is overwhelming most people. So one of the things I found critical is you learn a lot by hanging out with people unlike you, so you don't get trapped in an echo chamber. That's how you catch new ideas. It's a version of what Bill and Tuck both said.
Great final point. We are now going to go to Q&A. So let me dig into our Q&A feature here. There's a few questions. Let's see which is the good. Let's see. Raghu asked, Dan, your well-written paper, HPC forecast cloudy and uncertain. You make a good case for many maxims, including bespoke systems and faster prototyping. Do they still hold true today? What's your latest perspectives on that famous paper you did, HPC forecast cloudy and uncertain?
Yeah, I think we didn't touch on that, but I would say one of the things that we really have to do is think hard about that low percentage of performance that we're delivering on lots of multidisciplinary applications. One of the opportunities, I think, is to build partially bespoke systems. Chiplets give us an opportunity to do some custom specialization there to optimize core algorithms. To do that, though, you have to build prototypes. And right now, outside of the private sector, I mean, Google's doing that like mad with TPUs and other designs. How we do that in the broader scientific and engineering community is an open question. We need an ecosystem to support that. That's actually an example where public-private partnerships could drive that forward. But right now, we're lacking.
All right. Another question from our audience. How much will power generation and access influence the next decade of HPC plus quantum plus AI research and development? So, Took, why don't we start with you on that as the Department of Energy representative on the panel?
I'll start. I think that is a key determining factor in how federal programs like mine procure systems, right? That have HPC, AI, quantum capabilities. Just because I mentioned the decreasing buying power, and so we'll have to my program for the last decade and a half, we have procured smaller systems at the 3 national labs and other NNSA sites, and so we are kind of weirdly now going from the high end of compute now moving toward the lower end of compute, so that we can service other NNSA programs that do not have the HPC ModSim expertise, but they just want to use AI to do their mission work. So they don't have big data center facilities to even host big systems, right? So this is where power as a factor is changing our business model already.
But Took, I want to build on a little bit. Do you see we're starting to see a resurgence in interest in nuclear, for example, and small modular reactors and things like that? Do you see over the next decade a significant change in the energy capabilities, generation and distribution coming that may address this?
Yeah, I think so. I think so. Especially, I think, so SMR has had its start from prior administration, but this administration has accelerated more, even with the permitting, front end. And so I think that will change the compute acquisition and facility operation models. For both federal government and private companies. Yeah.
Dan, you want to take this question next? How do you see the power generation and access influencing the next decade of HPC, quantum, and AI?
Well, if you told me a few years ago we'd be talking about megawatt racks, I probably would have cringed, but we are at that point. So I think there's some basic semiconductor and material science long-term research about more energy efficient materials and designs. That's beyond the scope of today, but that's a basic R&D question. The challenges around the electrical power grid and the proximity of placing, those are real issues. It's driven turbine generators in the short term for many of us to power systems. That's not an optimal environmental solution, but I don't see. As long as there is money to be made, scale will continue to grow. Maybe I'll leave it at that. But that's the place where I would say academia and government are facing a different challenge than the private sector does because of those economic dynamics. OpEx is a killer issue for many places now. And, we used to just talk about CapEx and view the energy as free.
And Bill, do you want to close out this question and the Q&A session?
Yeah, I mean, the original question was, you know, is energy a big concern, right, for the future? And I think the obvious answer is yes. It comes down to two things, really. One of them is, or three things. One is the efficiency of the systems. The other one is the overall demand and the pace it grows. And then the third is obviously the supply, not just the money side of it, but just how fast you can build things. And I think the industry right now, everyone would say, is constrained by energy. You know, I talked about building my first PC so I could run Linux, so I didn't have to dial into NCSA. You know, I did that in an afternoon. You can build a server in a day with the supply chain. You can't build a power plant in a day. And so we can't really control the pace, even if, to Dan's point, the money is there, the desire is there, the demand is there. There are some certain limits of just how fast we can go. And I think that's the constraint in the industry right now.
All right. With that, I want to thank all of you so much for your insightful comments here today. I encourage the audience to give them a meatmoji round of applause for sharing your expertise and time with our community today. This is going to be a great video. I'm sure many watchers of this as we post this later today or tomorrow. So again, thank you very much.